Good morning. So I'm going to take a little bit different approach to this. I'm not a data scientist. I'm an engineer, chemical engineer. I've been in the industry since the 80s and focused almost entirely in that time on automation and process control. So always been around this idea of data and analytics and so on and so forth. And what I have to bring to you here today is a little bit of discussion about the history of what's been happening with that and how that is applied today, and I think you'll see quite a lot of what's been going on. When I first started in the 80s, all of the instrumentation, sensors, and everything was analog, pneumatic, some electronic. But what was different at that time was we were starting to connect instrumentation to digital control systems. That was really just beginning in the 80s. And at that time, we didn't know what to do with all that data. There was so much data, so many alarms, so much information, and nobody really knew what to do with it. But they kept putting it in and historizing it and collecting it. And we'll see kind of what's happened with that. So I'll talk a little bit about, I guess I don't really need to talk about what is IIoT and why to consider it here, but applications of that to process control. Now, just to be clear, what I'm talking about with process control, this is the equipment and systems that control industrial processes, oil refineries, chemical plants, pulp and paper facilities, and that kind of thing. They measure something about the process, decide what to do with it, and then take some action, usually opening or closing a valve or adjusting the speed of a motor. So these are the control systems that we're talking about. So some basic definitions, and what I really want to focus on is over here. This is the Microsoft definition of IoT, or Internet of Things. It says you have these 5 layers, devices, some type of smart device, some connection to pull that data out, history, analytics, and presentation. So let's talk about what that means. Okay, Internet of Things is for, right, kind of simple presentation. When we think about it in a typical context, mostly people have started thinking about smart thermostats and smart refrigerators and smart cars and that kind of things in their homes. When we talk about it in the context of an industrial facility, we're starting to talk about things like smart measurements, pressure, temperature, level, and flow, smart devices to measure those things. We've been measuring those things for years and years. What's new, if you will, about smart devices is their ability to kind of diagnose themselves as well as tell us about what they're intended to measure. And then smart valves. So now we have valves. The company I work for is Metso. We make control valves. And anybody these days that makes control valves makes smart control valves that will measure and tell you things about that valve itself. For example, is it getting enough air supply pressure to operate itself? What are the ambient conditions around the valve? How much force does it take to open and close the valve? Those kind of things. So things about itself. And then we can think about tying all that information together to give us kind of a smart factory or smart unit operation, or indeed an entire smart refinery. So that's the context of Internet of Things as it relates to factories. So we start with simple devices and we work our way all the way up to a factory. So we start to ask the question, oh, and of course, smart people, right? Anybody wearing like a Fitbit or something like that? Maybe you're a smart person. Who knows? So, Internet of people. Okay, so when we talk about these plants, question is, do we already have the Internet of Things in industrial environments? Is it already there? Or is it something we have to go buy and install and start? Well, let's talk about devices. Do we already have smart devices in plants, in oil refineries, chemical plants, factories? Yes. Smart instrumentation has been around in these plants for over 20 years. Okay, for 20 years, we've been installing temperature instruments, pressure instruments, flow instruments that have some onboard intelligence about their own performance. They know, they have diagnostics, they have information about how they're performing themselves. And in fact, even if we don't have smart, so-called smart instruments, we have a lot of dumb instruments that are connected to a digital control system. And the control system itself can add a little bit of a layer of intelligence to those measurements. So for example, if we're measuring the temperature, I'll just use the temperature of this room as an example. If you have a digital control system controlling this room, which Probably we do. The temperature measurement itself is smart, or not smart, but the control system adds a layer of intelligence on top of that. It might measure the average temperature of the room, the standard deviation, the variation in it over time, whether it's different in the daytime or the nighttime, how much load there is on the room. When more people come in the room, there's a lot of heat generated, so it maybe is detecting that. And that control system is adding that layer of intelligence. Is this mic working okay for you all? Okay. So, in fact, we have had for many years devices, smart devices already in the industrial environment. We don't need to go buy some new devices to have the industrial Internet of Things, because we already have thousands and thousands of smart devices typically in a typical plant. So what about connectivity? This one's a little bit different. In connections, there are many, many, many different ways to digitally connect the information from all of these smart devices in the field in industrial facilities. There are many standards, which means really there's no standard, because there are many standards. And this information brings all the data into the control systems and ties it then into sometimes into asset management systems and historians, and we'll talk about some of that coming up here. And so the information is digitalized. However, and this is a really important point, and I'll come to it again in a couple of minutes, that doesn't mean the information is available to us in the Internet. And we'll be asking the question in a minute, do we need the Internet to have the Internet of Things? All right. So cybersecurity is a huge concern for these type of facilities. It's one thing to say, I would like all the data from my plant to make it to the cloud. It's quite another thing to say, I would like to have a connection from the cloud down to my plant floor. Okay, especially when you're talking about something like a chemical factory or an oil refinery or power generation station. Okay. History. Starting in the early 90s, most of these plants started installing data historians, collecting data at fairly high frequency and storing it. Not really sure what to do with it yet, but we collected a lot of data and we've stored it, starting in the 90s. Huge amounts of data. Once per second data, if you can imagine an oil refinery with maybe 10,000 online instruments collecting data at once per second. That's a lot of data. So there's no shortage of data stored away in history somewhere. Analytics. So analytics was an area where there wasn't a lot of attention placed over those years, in the 80s, in the 90s. And we started to see clever engineers coming along, building some homemade tools, using the control systems to do some calculations, do some predictions. We saw in the earlier presentations talking about, for example, fouling of heat exchangers. You know, in the 90s, I remember writing a small application to detect the fouling of heat exchangers, loading it on a control system, and providing that advice to operators. So those things have been around for a while, but just not widely disseminated. And it was very difficult for many years to replicate that kind of analysis and take it to another plant and install it there or commercialize it. So there were a lot of homegrown tools, people working with spreadsheets, people doing some very clever things, but these were fairly limited by the commercial platforms that were available at that time. But still, it was out there. And then we started seeing some vendor solutions coming out, and these days there are more and more of these kind of tools for analytics. And then lastly, the presentation layer, when we think about reports and dashboards and all of those kind of things. What I find is typically in this environment of industrial automation, people tend to think mostly about the devices and the presentation layers when they think about industrial Internet of Things. I have some device, I can see it on the dashboard. This is measuring my heart rate. I can open my cell phone and see my heart rate. Okay, and I kind of forget about everything that's in between, those connections and analytics and so on. But we need all of these layers. Now this is an interesting slide. If you think about all of the data that's generated by various industries. This was a study by McKinsey. Government, banking, retail, so on and so forth. You think about all those industries, which industry generates the most data? It's manufacturing. And it's manufacturing by far. Think about that. Twice as much data as government. So that's a huge number around the world. And again, the challenge is going to be, what are we doing with all of that data? Yes?
We'll take questions later, or? Yes.
I'll take questions at the end, yes. So, we've had all this data. We've had this for a long, long time. About midway through my career, we started using this data to start analyzing what's really going on in the plants. What do we really know about our facilities? We have such huge amounts of data. Have we turned that into some useful and actionable information? And surprisingly, or maybe unsurprisingly to this crowd, the answer to that is no, we didn't really do as much of that as we should. What we found when we started analyzing these plants is that the control systems themselves were really not doing their jobs. That's kind of surprising. So if we think about that, I'm going to give you just a little terminology to make sure everybody's up to speed on the same thing here. I'm going to talk about control loops as a way to measure this. A control loop is the entire process of managing one variable in a plant. So if we're talking about the temperature of this room, it's the temperature sensor, the controller, and the valve that opens or closes to put, apparently, steam into this room. All right, okay. And so that control loop, so it measures, it decides what's to do, it opens or closes a valve, adjusts the temperature of the room, then it measures it again, and this goes round and around in a loop. A typical plant, let's say a pulp and paper facility, a paper machine, is somewhere between 200 and 500 control loops. A typical jetliner, if you think about a jet as a process, has about 100 control loops: fuel flow, airflow, engine temperature, hydraulic pressure, so on and so forth. If you think about an oil refinery, we're talking about 3,000 or so control loops per oil refinery. What we found is this. The things in our industrial Internet of Things were pretty bad. Typically, about 30% of the controllers in a plant are operating in manual mode. That's quite shocking. Imagine going to the door of the aircraft, talking with the captain, and saying, how much of the plane will you be flying on manual today? And he says 30%. You really have to think twice about whether you're going to step into the plane. You know, which 30%? The fuel flow? The hydraulic pressure? Which part are you going to be adjusting things while you're trying to land the plane? You know, so that's quite concerning. In an oil refinery, typically that's not the problem. That's the symptom. It's a symptom. Controllers are put in manual for a reason. Usually the reason is something else is not working properly, right? So if the temperature of the room is not working properly, what are the manual controls what do? We turn off the thermostat and we open the door, right? That's in manual. It's in manual, but why is it in manual? Well, because something wasn't working properly. 30% of the controllers have horrible tuning. So tuning is telling the controller how fast, how much do you need to react to take control of the process. So for example, the tuning of the temperature in this room, if we had really strong, aggressive tuning, the air would come on full bore, cool the room down, but maybe a little too much, and then it'll have to warm it up a little bit, and then cool it, and warm it up. Really, I think about this like trying to teach, how many people have ever had to teach someone how to drive a car? Right? Yeah, okay. So you know, sometimes you're teaching a teenager to drive the car. Sometimes they're controlling a little too much. Sometimes not quite enough, and they're drifting off to one side or another. So the tuning is getting that right, getting that balance right. How much action do you need to take to get the process back under control? What we found is about 30% of controllers had absolutely horrible tuning. Horrible tuning. In fact, about 10% of controllers we found out in plants still had default values in there that were put in by the control system manufacturer. It's quite surprising. It's quite a big number. And you wonder why 30% is running in manual. 20 to 40% of the plant is oscillating. It's wandering, just like this. So imagine, you can think of this like the car as well. If the car is going down the road like this, if you're staying in between the lines, everything's okay, right? Right? Are you okay with that? If the average value, that is, I'm staying in the middle of the lane, is okay, is it all right that I'm wandering like this? Is it efficient? What do you think? No, not so efficient. Is it safe? Is it causing some reliability problems for the car? Am I wearing the car faster? Yeah. Same thing if I had the cruise control on, and the cruise control, instead of holding steady at a constant speed, was going up and then down and then up and then down. Well, you know, I'm sorry, officer, but on average, I was under the speed limit. Is that going to work? Probably not. Right, so same kind of thing. So we have this oscillating problem in plants, and then we also have some mechanical problems around the control valves. Typically about 30% of the control valves have some mechanical issue. It's too big, it's too small, it has mechanical stiction or looseness in the valve. So you can think about that, for example, if a control valve is too small.
But also, this is good, right?
Uh-oh, we're getting a little bleed through. If the control valve is too small, what will happen? Like, let's say we're trying to make this room cooler, and there's a valve with some cooling water going through it, trying to make this room cooler. But the valve is too small. What will happen? The controller will keep telling that valve to open. Open some more. Open some more. Open some more. And eventually, that valve is fully open. It's putting as much cooling water as it can into the coils to cool this room. And then what? Still not cold enough in here. So what happens? Nothing happens. Nothing more can happen. The valve's already 100% open. That's all it can do. So what happens is now we have no control. Okay? We just have to live with whatever temperature it is. We're at the limits of what the plant can do. We have no control over the process. Okay. If the valve is too big, we have other problems to make it hard to control. What does that mean to the plant? Well, it means that in the plant, we wind up increasing the performance of the process, or increasing the variability of the process. If you have these control problems, you will increase the variability in the process. That's a real problem for somebody like me who's been for 30 years trying to improve control in process facilities. Why? What is the job of the process controls in a plant? What's the purpose? Why do you even have a control system? Why not just put in everything without valves and instruments and just let it run? What's the purpose of a control system? It's to reduce the variability, to stabilize the plant and to reduce the variability. And yet, it's not on this number's not on this slide. 75% of controllers in plants do not reduce the variability of the plant because they have some of these problems. So we're operating in a very target-rich environment, okay? Which means there's a lot of places we can make improvements. The problem is, even though we've been collecting this data for all these years, most plants have not been doing the analytics to understand where the opportunity is. If you walk into most plants in the world, nobody knows how much of your plant is operating in manual today. How many of your valves are too small? How many of your instruments are saturated? Saturated instrument means like your speedometer on your car is pegged. You're driving so fast that it's at the limit. And again, once you're at that point, now you don't know how fast you're going. Okay. So there are opportunities to improve the performance of the plant if we pay attention to those analytics, and especially, I'll get to in a minute, if we prioritize. Because if 30% of the plant is in manual, that's a lot. It's going to be very, very hard to deal with all of those. Okay. A little bit about the cloud. I talked about this before. So a typical IoT application, like a Fitbit, I have a device, it's connected somehow to the cloud, and in the cloud then I can do some kind of analytics. And I can also, from my cell phone, I can make adjustments to the settings on my Fitbit so that I can put my preferred settings, make it be larger text so I can see it these days, do all of that kind of thing from adjusting from the cloud. In the industrial world, we have some smart devices, but here we start to run into problems. The nasty cybersecurity concern again. Most of these plants are really concerned, terrified, in fact, about making a connection between a field-connected device that somehow, some way, is connected up to the cloud. They might be okay about the data from that device getting to the cloud, but they're very, very concerned about there being a connection that allows somebody, somewhere, to come down to that device and make a change to it. Okay? Rightfully so. Okay? We don't want these plants to start blowing up around the world. And there are many agents around the world who are intentionally trying to hack into these control systems and take control over them and make some change happen. In a lot of cases, those are our own governments doing that, and in other cases, it's other actors doing that. So there's a real concern here about doing this. So I will allow this within the plan, allow the data to be collected. Not so sure in a lot of cases, some people are saying, I'm not so sure about passing that data up to the cloud. Somebody might find my information, let alone, right, all of the company's information is already in the cloud, their payroll and customers and prices and everything else that's secure, banking, everything else that's secure, but somebody might want to know what temperature we run tray number 3 of our distillation column, so we don't want to put it up there. So that's a concern. Still, we're in many ways in the automation industry, we're very ahead of the times, and in many ways we're quite a bit behind the times sometimes. But definitely this is a concern. Bringing some kind of action from the cloud back to the plant is a big, big concern for a lot of these folks. So what has happened is many places have resorted to kind of an on-premises Internet of Things. So it's really kind of an intranet of things, if you will, where we bring the data in to some device, perform all of our analytics here, keep it within the plant, maybe pass some data out from there to the cloud if we can find a secure way to do it. And again, and then if this is all on premises, then we're not so concerned about getting data back down to the device. So this is kind of the de facto state of the world right now with industrial IoT, a lot of emphasis on the on-premises part of IoT that is doing everything you need to do within the confines of the industrial environment. Now, I come back to this slide because I really want to emphasize where things are at here again. Devices. We've had smart devices for years and years and years, over 20 years. We've had smart devices driving the data up. Sometimes not so smart devices augmented by contacts putting the data in. We have many different ways to connect and bring data into a digitalized system. Those have also been in place for a long time, as has the history. But the big opportunity here is in the analytics, is in using the proper analytics and applying those to the plant en masse. Okay? So how do we find those 30% of controls that are in manual, those instruments that are failing, those valves that are failing, so on and so forth? There's plenty of opportunity to make improvement to the plant if we only know how to do that. So I'll give a few examples of what's being done with this, some practical examples of where this is being done. So this is a trend showing a flow measurement. So this is a flow meter, and it's hard to read the scale from where you are probably, but this is something like 600 gallons per minute on average up here. But and then the blue is the valve position, but the red is the flow. So what's going on with this flow? It's running along at about 600 gallons per minute, and then it drops down to about 100 for about a second, and then it goes back up. And then it keeps measuring along, and then it drops down to about 100, and then it goes right back up after 1 second. So what's going on? Is the flow in the plant really going from 600 gallons a minute down to 100 gallons per minute for 1 second and then popping back up? No. You can't get the flow to stop that quickly. So what's happening? The instrument's failing. Okay, the instrument's failing. This is a failure mode of a typical magnetic flow meter. It's one type of flow meter that over time, the lining on the meter starts to fail. As the lining on that meter starts to fail or develop bubbles in it, you'll get a spike in the measurement. It'll just drop out, just for 1 second. Sometimes it goes to 0, sometimes to a low number. It just drops out. And then over time, as it gets closer and closer to failure, this frequency starts happening more and more often. So what happens at first is the operator will get a low flow alarm. We'll say, the flow stopped. And then they'll go look at it, and they'll say, no, it's not. It didn't stop at 600 gallons a minute. Okay? But you see this pattern. So this is telling us that an instrument is failing, and we can predict that a mag flow meter is going to fail when we see that. I'm going to get through these slides quickly here. I'll move on to another one. This one is showing us a different kind of problem. So here's a flow going through a valve, this red line again. And here's the valve position. So what's happening here is the valve is sticking. So the valve is trying to move. It's being told to move. Nothing happens. Move. It doesn't move. Move again. Doesn't move. Move again. Still not moving. Move. And it moved. Now it unstuck. And then it's told to go the other way because it went too far. Move. Doesn't move. Doesn't move. Doesn't move. Finally it moves. So the pattern that we see here, okay, we can apply some analysis here to find out what's going on. When we see this kind of square-shaped pattern on the red, that's the flow, and this kind of shark fin pattern on the blue, or the commanded valve position, we know right away that's a sticky valve. I can tell you with about 99% certainty that's a sticky valve. And I can confirm that even further by plotting this process variable versus the control output and seeing this kind of characteristic pattern we call steps on a ladder. So this is another type of predictive, well actually it's not even really predictive, it's telling us we have this problem right now in the plant and we need to go solve it and fix it. So the analytics are going to tell us an awful lot about where we have the problems, what kind of problems we have. I can do about 80 types of analytics now on control loops. The challenge then becomes, just as was mentioned in the last presentation, the ticketing and the follow-up and the service that's required to get these things fixed. You simply don't have time to fix everything. In an oil refinery with 3,000 control loops, you're going to have about 900 things that need to be fixed. Which 5 can we work on this week? That's the real question. Prioritization, merging economic information with this kind of technical information is critically important to get us to that point. So that's, if we take analytics a step further, one of the other things we can do here is look at not just each individual controller, but if we start thinking in a big data sense, we start looking for interactions between controllers in a process plant. Again, the earlier presenter talked about these process plants being very complex environments where a change in one area has a ripple effect and carries on throughout the plant. So if you think about, for example, the steam production in a boiler in the utilities area of a plant, that affects every single part of the plant that uses steam. If the steam temperature goes up and down, then everything else in the plant that uses steam is going to follow that pattern. So if we apply some big data kind of approaches to this, what we can do is look for the root cause of upsets in the plant. And the way we do that is like what we used to do in the old days. We used to take out paper strip charts of temperatures and pressures and flows and lay them on the table, look for similar patterns, put them together, hold them up to the light and shift the pages. Well, now we do that kind of thing electronically to find the root cause of where things are. Very often in a plant, the root cause of a problem may actually be half a kilometer away in another part of the plant. So it's been a really interesting learning process as we've gone through that. And I'd be happy to talk to people about examples of that. as well.